All right, so yesterday we dealt with direct variation and joint variation. Today we're going to look at a couple other things. One is called inverse variation, and the other one is, I think, compound variation. But with the inverse variation is the opposite of direct variation. With direct variation, we said if x gets bigger, y gets bigger. If x gets smaller, y gets smaller. But with inverse, then the inverse thing happens. So when x gets bigger, y is going to get smaller, and when x gets smaller, then y is going to get bigger. So if you look at the rule for inverse variation, which is y equals k over x, what happens, since x is in the denominator, that means we're dividing, right? So when I divide by a larger number, I get a... So as the number I'm dividing by gets bigger, my answer gets smaller. And if the number I'm dividing by gets smaller, the answer gets bigger. So hence we get the inverse variation. Okay? And this is of the parent function y equals 1 over x. Inverse variation, which we've done some of in the past, and that's mostly the things we're going to be working with in this chapter, deal with inverse variation. All right, so we're going to write and graph inverse variation. Now, we learned with direct variation that we could find a pattern to find k. In direct variation, we said we could divide y and x. Well, what can I do here to solve for k? Okay. Multiply by x. So if I'm doing inverse variation, which is y equals k over x, then k is going to be equal to x times y. So if we want direct variation, we'll take y and divide by x. If we want inverse variation, we'll take y and multiply it by x to get the value of k. So here this says y varies inversely as x. So as soon as I see this, I know that I'm working with an inverse variation. Y equals k over x is the situation. And it says y equals 4 when x equals 5. So to find k, I'm going to multiply 4 and 5 together. So k equals 20. So my function is y equals 20 over x. Let's see if it likes me. Nope, I didn't write it fast enough. All right. Now, graphing y equals 20 over x. All right, let's find some easy numbers to graph. What's a couple of easy numbers that go into 20? 2 and 10, right? Okay, 20 divided by 2 is 10, or 10 divided by 2 is, or 20 divided by 10 is 2. Okay, and also 4 and 5, right? Okay, let me make my graph a little bit bigger here. 1 and 20. Yep, 1 and 20. All right, 1 and 20 aren't as easy to work with, though. Okay. So we know that we have the points then. If I do 20 divided by 2, I get 10. Oops. If we do 20 divided by 10, we get 2. Okay, so I'd have those 2 points. 4 and 5 also, right? Okay. 20 divided by 4 is 5. And 20 divided by 5 is 4. So our graph is going to come down here like this. Okay. So the graph will actually look like this then. Okay. Now, is this graph going to cross the x and y axis? Okay. What happens if I divide by 0? What do I get? Okay, it's undefined. So we actually have asymptotes there. So these graphs will come down here, but they're not actually going to cross the x-axis. And make sure that you put your arrows on the end of these when you graph them. Okay. All right, so we have up here where they're both positive, and then if I put it down here, it's when they're negative. So all of your direct variation problems, when you graph them, it's going to be a line that goes through the origin with whatever k is the slope. All of your inverse variation are going to look just like this graph here. The difference is which points are you actually using for it. But make sure that you do not cross the x and y axis because those are asymptotes. And we'll talk more about them later on. All right, so I want you to, so as we had the proportion for direct variation, there's actually a pattern like that for inverse variation, because since y equals, or since k equals x times y, then I can actually write this multiplication for inverse variation. It says x times y equals x times y. So our first scenario, x times y, equals the second scenario. So you can do it two different ways. Just like we did with the direct variation. You can find k first of all and then plug it in, or you can set up this situation with x and y to be able to do it a little bit faster. So here, the time needed to complete a certain race varies inversely as the runner's average speed s. So here we go. There's the first thing I'm looking for. It says varies inversely. Time to speed. So when I set it up, I have that time is equal to k over s. Or, as they've already written it over here, time sub 1 times time times speed is equal to time times speed. What is that? Tell me. Really, what does time times speed tell you? Okay, it tells you distance. Okay, how fast you're going, time multiplied by how many hours you travel or minutes you travel is going to be equal to the distance. So here it says a runner with an average speed of 8.82 miles per hour completes the race in 2.97 hours. So 2.97 is equal to k over 8.82. So to find k, we multiply those two numbers together. And so I'm going to get something around 27, right? A little less than 27. What is it? 26 point what? 23. Okay. So they went 26.23 miles. Any runners in here? Cross-country runners? All right. Does that number mean anything to you, Sam?
It's a marathon.
That's the distance that he ran. Yep. All right. So that would be, that's a marathon. So apparently he's running a marathon because this is the approximate distance for a marathon. Okay. Somewhere around there. Yep. So. Okay, so he says, what is the average speed of a runner who completes the race in 3.5 hours? So our time is now 3.5. The distance, or k, is 26.23. We need to find s, that person's speed. So how do we solve this for s? What do we have to do?
You 3.5 divided by
The problem is that our variable is in the denominator, right? So we need to get the variable out of the denominator. So to do that, I need to multiply by it, okay? So we need to multiply both sides by s. Now that gets the s out of the denominator. So now we have 3.5s is equal to 26.23. Okay? So then we just divide by 3.5 to find our speed. And this is going to be an approximate speed, not an exact value. Okay? 7.5 miles per hour. Okay? So that's the first method you can use in solving it. And just like with the direct variation problems, probably using that proportion is a little bit easier cross multiplying. Same thing here. My time one was 2.97. My speed, 8.82. My time two is 3.5. All I need is to find the second speed. And so much easier here. Divide both sides by 3.5 to get your approximate speed of 7.5 miles per hour. And don't forget your units. Okay? Definitely method 2 much easier than method 1 in the inverse also. So if you have an inverse variation problem they want you to solve, then you'll be a little bit farther ahead by just solving it using this method here, method 2. All right, we have 2 other ones we're going to look at. So one thing is we're going to look at how do I know what a set of data is? Is it direct variation or inverse variation? And here they're just reminding us of some things that we've talked about already, that if I have direct variation, oops, that's not what I want. If I have direct variation, then we know that k is equal to y over x, our constant ratio. And if it's inverse variation, then we have k equals xy, which they call our constant product. Okay? Constant ratio and constant product. So if you have a set of data and you're trying to decide whether it's inverse variation or direct variation, you have the option. You can first divide y and x, see if they're all the same, or multiply y and x and see if they're all the same. Stephen? So hopefully a lot of these, when you look at it, you're like, okay, you can see it right away. All right, if I divide them, I'm going to get the same answer. If I multiply them, I'm going to get the same answer. Not always, but you probably can. So here we want to know whether these sets of data represent direct variation, inverse variation, or neither. So I will multiply x and y and divide y by x to see which ones give me the same value. So let's start out, multiplying is always easier, right? So let's multiply first. What's 6.5 times 8? 52. Okay, 52, right? 6 times 8 is 48. Half of 8 is 4. 48 plus 4 is 52. So I multiply these, and I get 52. 13 times 4 is 52. Half of 104 is, okay? So since k is equal to x times y in this situation, then this problem represents an inverse variation. And like I said, hopefully when you look at them, you have a pretty good idea. Now in this situation, and the other thing is this, okay? That when we talked about them, inverse variation, as x got bigger, we knew that y was going to get smaller for inverse variation. Okay? Or as x gets smaller, y should get bigger. And that happened here. As x got bigger, y got smaller. Okay? If it's direct variation, if x gets bigger, then y gets bigger. If x gets smaller, then y gets smaller. All right, so when we look at this one, 5, 8, and 12, 30, 48, 72. So x is getting bigger and y is getting bigger. So I know it cannot be inverse variation. So I need to check direct variation. I need to see, is k equal to y over x? So if we divide, 30 divided by 5 is 6. 48 divided by 8 is, or 6. And 72 divided by 12 is 6. So when I divide, they're the same. So that means I have direct variation. Well, except it's y over x, not x over y. But yes, it will work. Okay? You'll still get the same number when you divide it. Okay? Okay? All right. Letter C. So I look at letter C. The x values are all getting bigger. Okay? I look at the y values. Are they getting bigger or smaller? Okay, they're getting bigger. So I know it can't be inverse variation. So I need to check to see if when I divide, I get the same values. So we get 5/3, 14 over 6. Is 5/3 the same as 14 over 6? If it was, then this would be a 10, not a 14, right? Correct?
Can't do it already. It's done.
Okay. So this one can't be direct variation then, because that fraction's not the same. So this one would be neither. All right, as long as two of them don't match, you don't need to worry about the third one. Okay, so check these two. Okay, so the last thing is then is combined variation. And combined variation actually uses all of the above. Combined variation looks like this, that y will equal k times x divided by, z, excuse me, z's in the denominator. K is the constant of variation. Since x is in the numerator, that means it varies which way? Directly or inversely? Okay, directly. And y or z is in the denominator, which means it's going to vary inversely. So anything that varies directly will be in the numerator. Anything varies inversely will be in the denominator. Okay? So here's our problem. The change in temperature of an aluminum wire varies inversely. So let's get our highlighter here. Inversely as its mass and directly as the amount of heat energy. So since the mass is inversely, it's going to be in the denominator. Since the amount of heat energy is directly, it's going to be in the numerator. So here we have the change in temperature, which they're using I, is equal to m oops, let's see. M is in the denominator because that's inversely, and K and E are in the numerator because they are directly. Okay? Anything directly is in the numerator, inversely is in the denominator. So it says the temperature of a wire with a mass of 0.1 kilograms changes let's see, temperature I of an aluminum wire with a mass of 0.1 kilograms rises 5 degrees Celsius with 450 joules of heat energy are transferred. So we've got our M is 0.1, so that's our denominator. The temperature rises 5 degrees, so that's I. And when 450 joules of heat energy, that's E. And so we need to use that information to find our constant of variation K. So you have two choices here. You can divide this by 0.1 first. And then divide, or you can multiply by 0.1 and then divide by 450, either way. Let's see. 450 divided by 0.1 is 4,500. Right? If we're dividing by 1/10, that's the same as multiplying by 10. Okay? So then we divide by 4,500. Okay? Now, we could change it to a decimal. I like a fraction in this case. How many times is 5 going to 45? 7, really? All right, okay. All right, I think 9. All right. So K, in this situation, K is equal to 1 over 900. All right. So 1 over 9 is 0.111111. Okay. So 1 over 900 would be 0.00111111, right? Let's just check our calculator here. 1 divided by 900. Okay. I just want to make sure I'm still doing my math right. So this is equal to 0.00, or 1 with a bar over it if you want. So it says how much heat energy, so we're trying to find E, must be transferred to aluminum wire with a mass of 0.2 kilograms and raises its temperature 20 degrees. And we have 0.001 here. So how many of you are really smart? All of you, yes, good. Okay. 0.2 times 20 is 4, right? 2 times 2 is 4. So 0.2 times 20 would be 4, correct? Okay. So here we have, now, isn't this 1 over 900? 0.00111111? All right, so how do I get rid of that 1 over 900? Oh, multiply by 900. So E is equal to 3,600, and that is, don't forget your units, which in this case is joules. So in other words, if you did 0.001 divided by 0.2 and then worked with that with 20, you would get 3,600, however you do it. I just like the fact that I can do it without a calculator. Okay.
How do we get 3,600?
All right, I multiplied by 0.2, and I got 4. Okay. This number here, 0.001, is 1 over 900, Okay, so I changed it back to 1 over 900. And then to get rid of this 1 over 900, I have to multiply by 900. 900 times 4 is 3,600. Okay? All right, so